Thank you for having me. As Robert said, I'll be doing a presentation on foundation models, but also how these can be used in some concrete ways that we're doing it here at the Phi-Lab. So very briefly about me first. So my name is Casper. I'm a researcher in the Phi-Lab here in Frascati, just south of Rome, where ESRIM is located, which is the Earth observation arm of ESA. I studied what is in Danish called landinspektør, and I imagine it's something similar in Norwegian as well, maybe landmåler or something similar to this. But I did an industrial PhD on Earth observation and artificial intelligence for global development, funded by the Danish Innovation Foundation. And I've been working on global development projects for quite a while. Here at the Phi-Lab, it's actually also my main topic is working together with UNICEF and the GIGA initiative on mapping schools all over the world using Earth observation and trying to estimate whether they're connected to the internet or to the power grid. And to help me achieve this, we're using various foundation models and investigating it here in-house at the Phi-Lab. But we've also initiated several ITTs on foundation model. One of them is the foundation models for climate science, which I know the University of Tromsø is a part of. And we've created a framework in-house as well for evaluating these foundation models. But it's not I must say I'm not an expert on foundation models, but we use foundation models and we're investigating it quite heavily here in the Phi-Lab. Yeah, I included the image on the far right because I went to Svalbard a few years ago and it was great. So I've been to the Arctic, which was a very cool experience. I also work on doing socio-demographic mapping using Earth observation. So this is doing population estimates, figuring out the wealth in a given area, trying to help financial institutions figuring out where to build bank branches, where to send mobile money agents, and these kinds of studies as well. Briefly about the Phi-Lab itself, which is where we're located together with Nikolaus and Luke, who's also in the comments. So I sit in what is called the Explorer office. The Phi-Lab is an innovation lab as well, divided into two. So we sit in one big office. The Explorer arm is predominantly researchers. So we are currently 8 postdocs. We are a bunch of visiting researchers. And we have visiting professors as well. And we're investigating different topics that are related to the interests of ESA. So a lot of this, because we're in ESRIN, are related to Earth observation and the application of AI to Earth observation. But we're not an AI lab. We look into quantum computing as well. We have some people working on neuromorphic computing. But I think like 90% of our projects are somewhat related to artificial intelligence. We are connected to the other side of the office, which is the Invest office, where the InCube program sits. They sit on a big bucket of money that they do co-funding for European companies that are interested in doing de-risking of Earth observation related projects. And the researchers, help them evaluate the bids coming in from these companies. And if things come out of the Explorer office that could be relevant for companies, we might do the connection in this way as well. So we are two sides of the same idea of trying to create innovation in the Earth observation field in Europe. We're only about 35 to 40 people, a relatively new department. And yeah, as I mentioned, around 50% of us are researchers, and the majority are working on AI. So let's move on to foundation models. So I'll talk a bit about foundation models first, and different pre-training tasks and what they can be used for. Before at the end, I'll talk a bit about how I use it in my project together with UNICEF and ITU. ITU is the International Telecommunications Union, which work together with GIGA to do these connectivity maps. Together with UNICEF, sorry, the project is called GIGA. So if you look up online what a foundation model is, you will find many definitions of this. It's a running joke in the office here that by now everything is a foundation model. Anyone calls everything a foundation model, but what is it? What is it actually? And I think this is quite a difficult question to answer, and I don't necessarily have the true answer to this. And maybe some people in the audience have a better guess at what this is, how we should define this. If you create a generic definition of this, it could be this, that it refers to broad applicability and that it can serve as a base for more specialized applications. If it doesn't serve as a base, it should be able to perform a wide range of tasks without the need of training from scratch. Sorry. So it's very fundamental, this part, that reducing the need for training. So a foundation is something we can build on top of that reduces and creates a better starting points for what we want to achieve. But if we just follow this definition, then couldn't you make the argument that this is a foundation model? If you just take a data set like ImageNet that has labels, and you takes like a modern transformer-based architecture, don't you have a foundation model? And I think you could argue that you kind of do. I mean, some could call it a backbone, or you could call it many things, but it's kind of like a foundation model. My definition of foundation model is kind of a continuum. A foundation model can be more foundational than other foundation models. But there are many things a foundation model can do that makes it more foundational. So in essence, if we use this as a backbone that reduces our need for training in the future, then that's great. We can use it for transfer learning. We can create foundation models that are multimodal. We have a project here called FastEO, together with an external consortium, or an external consortium is running this, where we're also including text and other modalities of different satellites into the same models and being able to analyze these all together within one model. It could also provide zero-shot context. So let's say we organize our embeddings in very meaningful ways. So you click on one image of a windmill and you find all the other windmills or places that look similar to this, or you cluster windmills into different types using only the embeddings without doing any training, or you use text to prompt these models to figure out to do this clustering for you. And then these models, of course, ideally should be scalable and versatile, that we can use them for many different things. And there are many other things that these foundation models could do. There are many foundation models out there for text, for computer vision, and especially for Earth observations is still relatively new. And a lot of them are using similar methods to create their big pre-trained models. So possibly the most famous one out there currently is Prithvi, which is trained by NASA. It is trained using masking, so removing parts of an image and trying to predict what was in that image. Same goes for the Clay Foundation. And we have all of these other ones as well. There are the SATLAS, which we have a lot of labels, and you can pre-train a model in a supervised way, and you can use this as a foundation to build on. We have our own internal suite of foundation models called the Filio suite. We also have the Filio bench, which is what we use to evaluate the foundation models. These are trained in a semi-supervised way. It's a bit controversial whether or not it's self-supervised or semi-supervised, so I just put semi-supervised here to cover my bases. And then we have, well, here I wrote FastEO and Foundation Model for Climate Science, which are two consortium working on creating foundation models for ESA at the moment. There's a third project called the Represent, which are working on different self-supervised tasks, which could be used for foundation models. But similar to a lot of these models I just mentioned, especially the more traditional ways of doing masking, is something we wanted to investigate if we couldn't do better or differently in the Phi-Lab, because geospatial is special in the sense that an image is not just an image. We know where an image is taken, and it's a physical representation of what is going on the ground. And this gives us a lot of additional information that we can use to create our models. It also allows us to bring in a lot of additional data sets, like what is the terrain like in this area? What's the climate like? What's the biosphere in this area? How much water in this area? Well, water maybe is maybe not so static, but some of these more static data sets we can definitely use. So we use this metaphor for foundation models about the kitchen and making a croissant. So let's say you are asked to make a croissant, but you have never been in a kitchen before. You will likely do a very bad job. But let's say you are a chef that has done other things, but you've never made pastries before. You're likely to do a much better job at making a croissant than someone who's never been in the kitchen and have tools available for you to make something like a croissant. General idea of how to do this. So the idea is that we train these models to have generalizable features that we can use for other downstream applications. The initial idea here was that we could investigate different pre-training tasks that are trained in different ways. So we could take masking, removing parts of an image and predicting what was there. We could mix up the order of the spectral bands and train it to put them back in the right order. We could do geographical aware learning, where we train the model to predict where an image was taken, which climate it was taken in, or maybe the biosphere, some of these other ways we mentioned before. And we create experts or smaller foundations for each of these, train them separately, and then we create a meta model that will that can take the output of all of these models and decides which ones are the most the optimal one to use for your downstream application. So not just mixing them together, but the idea is that you could actually turn some of these experts off completely and just fine-tune the expert that is most suitable for your downstream task, or create a mix of these experts together. And by then you could create, start with a very big foundation, and then you could save a lot of compute power by just using parts of the the foundation that is most useful for your task. The current approach that we are using is described in this diagram. So we started with Sentinel-2. We're looking into using Sentinel-1 for this as well. But we're taking Sentinel-2 and we're taking all of the metadata that we have for Sentinel-2 and where the image was taken. And then we're testing all of these different pre-training tasks and how well the pre-training tasks do for downstream applications. So we do image reconstruction. We try to predict where the image was taken. We do some contrastive learning as well. And each of these experts then learn different domain knowledges, parts. One will know about terrain, one will know about location, and they will be able to extract different features that we can use. We test these on a large data set that we prepared for the Phi-Lab bench, where we are doing building density estimation, we're doing land cover classification, and we are doing road segmentation. And these are all part of the same data set. They're not separate data sets. They're one set of images covering most regions of the world, where we have big labels for these, meaning that we can cut them in any different patch and tile size we might need to test and evaluate these foundation models. Let's just see where I am. Okay, so I mentioned these traditional masking approaches before. This is also something we've investigated. Traditionally, I think one of the first tasks, self-supervised tasks that was out there was doing jigsaw puzzling, where you divide an image into different patches and you scramble them around and you train it to the model to put it back in the right order. Now it seems that we've more or less converged that most autoencoders, masking in general as a strategy, works quite well. There are some papers out there that not just masking, like removing the information, but replacing them with noise actually improves the masking process a little bit. But one of the things that we found that works very well was this geographical aware pre-training. And the idea behind this is quite simple. So some of you will probably have heard about GeoGuessr. It's this game where you are taken to a random place on the world in Google Street View, and you have to, I think you have, maybe you only have one guess, or you have 5 guesses. Oh, you do 5 turns, sorry. And then you guess where you are in the world. And then you get points for how close you are to that destination. Last year, there was the championships in Sweden, where this guy from the Netherlands won. The World Cup will be again in Sweden next year. And this gives these people working on this an immense knowledge about the world and what you would expect to see in different types of world, and they can tie it together. And this knowledge we can use in our foundation model. It's quite easy for the models to cheat, though, and especially for GeoGuessr. There's a very good illustration in GeoGuessr for how deep learning models can learn to cheat, just like humans can learn to cheat. This document C on the right is from what is called the Mongolia meta. So it's a document explaining how you can perform best in GeoGuessr for Mongolia. And it's all of these different things you can see in the image and where you might be if you see this in the image. So in GeoGuessr, you would look down and you would look, do you see a tent on the car? And if you see a tent on the car, and if the tent is white or if the tent is black, you are in different regions of Mongolia. So the model has actually not learned anything about the landscape. It has just learned to look at the car, and then it has already narrowed down the area significantly. This is something we need to be mindful of when we design these pre-trained tasks. So we trained a model on a global data set. This initial one was called the Filio Globe. This was just 0.5 terabyte of data spread equally around the world. We are currently training on Major Tom, which is 42 terabytes of data all around the world. And we are training the models to predict where the image was taken using, it's not just predicting the coordinates, but we're doing some encoding of the coordinates, but the essence is, in essence is the same. We're just predicting where the image was taken. So I just wanted to test quickly if you can do better than our model. So well, I can't see the chat, but if you can guess where this is, you would probably guess that it's somewhere in a desert. So it's in the Northern Hemisphere. This is the Northwestern Hemisphere, and it's actually in the Sahara. So this is what is called the Eye of the Sahara. And the model does very well at predicting this, even though it has never seen the Eye of the Sahara before. Same goes for an area like this. So you might have guessed that this would be somewhere in the Amazon, and it's correct. This is in Manaus, where the model is not completely accurately guessing Manaus, but it is guessing Amazon and Brazil. This is where the biggest what's called Pai River, or the 2 biggest parts of the Amazon flow together here at Manaus. This one, I was hoping someone in the audience might be able to guess, because this is in Norway. This is in Svalbard. And you should be able to see Svalsat here somewhere on this image. Yeah, so I don't know if you can see my mouse, but you can see Svalsat over here to the left with Longyearbyen hidden right there. So in order to test how these different foundation models do, we created this Phi-Lab bench, both the data set, but also a framework where you can put in a foundation model and we can tell you how well it does compared to other foundation models. And the idea for evaluating these is that we test them at different end shots. End shots meaning how many labels do you show the model and how well do you perform on a given task. So here, furthest to the left, I believe you're shown 50 labels. And if you're shown 50 labels, you do this well. And then the more labels you're shown, all the models luckily do better, the more labels they're shown. But as we increase the amount of end shots, the models also start to converge towards each other. It's not so evident in this slide, but you will. This is what you will see if you continue this further to the right. So our initial results here, testing our geo-aware approaches on guessing where an image was taken, does quite well compared to the masking-based approaches. That would be the geo-aware unit, fine-tuned, would be the dark green line here. And the red line is just a fully supervised one where you have randomized the initial weights. Here, Prithvi doesn't do so well, but it should say to Prithvi's defense that this is on Sentinel-2 data where Prithvi is trained on the harmonized Landsat and Sentinel-2 data. And that was quickly on foundation models and how we're thinking about it and testing it within the Phi-Lab. We currently have a foundation model for Sentinel-2 that is trained in this geographical aware way. We also have a model for very high resolution satellite data. And these models I'm both using in this project I'm going to present on profiling school catchment areas. So this is part of my research together with UNICEF on trying to map the location of schools. So the UNICEF ITU project called GIGA is about finding every school in the world and saying whether or not they're connected to the internet or the power grid. And then they have a lot of money and resources available to actually connect these schools to the internet. But you need to figure out where your gaps are in your data set, and you need to figure out how you can, in the most optimal way, connect these to the internet. So basically finding the clusters where you have a lot of people that are not connected, that can easily be connected through either fiber, satellite internet, or mobile internet connectivity. We're using a bunch of different data sets for this. Very high resolution data and Sentinel-2 are the most important data sets in this analysis. And what we're trying to predict is how likely is there to be a school at any given coordinate. So I give you a coordinate, and you tell me whether or not there's is likely to be a school at this location. And then we're trying to create a model on figuring out where we would have expected to find a school, but did not find one in our data set. To do this, we're using both a foundation model, but we're also the Sentinel-2 foundation model and combining it with what is called a multi-criteria analysis. Then for the two last ones, we're also using the foundation model. So how likely are there to be a school in these missing locations? So can we actually find the missing schools in the gaps in our data set? And for these schools we've then found and verified, can we estimate whether or not they're connected to the internet or the power grid? So this is being done in 4 different phases. So first we do a global analysis where we take all the schools from UNICEF. We look at population, we look at night lights, we look at buildings over time, and we try to create a statistical model for how many children should there be in a given area in order to there to be a school, and how far away from a school should that be, and are certain types of building more likely to be schools or not. And for this, we use traditional statistical approaches and random forest approaches as well. The method I'll show in a second is random forest. The population maps and the building maps we're using for these are derived from Sentinel-2 data. Then we're using the Sentinel-2 based foundation model to figure out in these gaps we've identified in phase 1, where are the places that are most likely to be a school. So we're not using Sentinel-2 to say this is a school or this is not a school. We're just using it to find the highest priority areas for where to look for a school. Because Sentinel-2 data is global, it's cheap. So we're using Sentinel-2 to do these large-scale analysis. And then once we have pinpointed the areas where we should look, we go to the very high-resolution data from tasking satellites, where we then look at these individual places and we say, is it a school or is it not a school? For this, we use a foundational pre-trained model for this as well. And then on top of this, we apply human-in-the-loop approach, which I'll show you in a second, where we train the model using an operator that tells us what is likely to be a school and what is not, and the model is continuously fitted on this data. And then at the end, we have UNICEF who goes on the ground and verifies whether or not these schools we've found are actual schools or not. So for the first analysis, this is the grid-based model. What you're looking at here is if a given area is red, it means our model has predicted there's a very good likelihood that there's a school in this area. If there's a black box around it, it means that there's also a population cluster in this area. So it's a high priority area because many people live in this area. If it's gray, it means close to a school. And if it's black, it means that there's already a school or sufficient amount of schools in this area. So this model is based purely it's purely tabular data, where we have summarized the statistics in each of these grid cells, and we are able to achieve an accuracy around 89% accuracy for this. This is then what is fed into the Sentinel-2 model. So I just wanted to mention Major Tom as well. Some of you might have heard of Major Tom. So it's a big data set that we recently released from the Phi-Lab by my colleagues Alistair and Miko. It's these 47 terabytes of Sentinel-2 data, and I believe approximately a similar amount of Sentinel-1 data that is that covers the whole globe, basically. This is what we are using to pre-train our, we do the geographical aware pre-training to create the foundation models for this next phase I'm going to present. We use Major Tom for this, and I suggest all of you to, if you're looking into doing something similar, please use Major Tom and check it out. It's a very cool large data set. There's a nice viewer as well, so you can see if your area of interest is covered in the data sets, but most places in the world are covered by this data set. So for each of these areas, we then pinpointed this is a high priority area. There's a lot of people and we think there should be a school. We then apply the Sentinel-2 model to say in this area, the most likely candidates to be a school is this area, which is what you can see in the small area here. I've only shown an example and not presented the accuracy yet because this model is currently being retrained. But the results for this should be done very soon. Then we do the very high resolution model. Again, we use the exact same strategy for geographical aware pre-training, but on very high resolution data at multiple scales as well. This is the sampling for this data set. For each point, we go from 30-meter resolution to 30-centimeter resolution. And we don't just train on predicting where the image was taken. We also pre-train on what the ground sampling distance is for each image. And this gives us a very good base. This model performs very well. And then we take our collected information on school locations and we predict whether or not there's a school in a given location. As you can probably imagine, it's quite difficult to say what is not a school if we're looking at buildings, because we don't have that in our data set. And if you choose points randomly, it's very easy to get super high accuracy, because if you choose super rural areas or you choose a forest, it's way too easy for the model to say that that is not a school. So in this data set, we use OpenStreetMap and named locations that are explicitly not schools as the negative. So this would be police station, churches, military areas, and so on are the negatives. So in this image you're seeing here, these are all 6 of them are actually schools. But it can be very difficult to say. We use what is called GradCam to visualize which parts of the image was important to make the distinction of whether or not it's a school or not. And it turns out that often the most significant parts of the image to say if something is a school or not is the area around the school, so the courtyard. So you'll see most of these schools, they will have a recreational field in front of it. So if you have a large building and a recreational field, the chances of something being a school goes up dramatically. We currently get 83% accuracy, which is good, not great. We hope we can make this better in the future. And we are continuously training this model by taking the data that I showed you from phase 1 to figure out where to look. Then we create an interface where the operator can zoom into these areas and interactively. So the model predicts as you zoom around the map where the schools, where it thinks there is a given school. And you can tell the model, this was a school, this was not a school. And then you can fine tune the model and you can see whether or not the model does better than what you're actually trying to do. This is also quite important to build more trust in the model, that this model is built together with operators and it's not just a one-time thing, but it's continuously fine-tuned. We didn't use a whole lot of schools to create these models. It's mostly the geographical aware pre-trained model that we're fine-tuning by just adjusting the last few layers to this specific task. But it doesn't have to be schools. We're working together with RTU on doing this on ITC infrastructure instead. And that was it for the UNICEF project. And at the very end, I just quickly wanted to mention that the Phi-Lab works together with a ton of external partners. We do a lot of ITTs, but it's also possible to come to the Phi-Lab as either a visiting researcher from industry or from a university. We also collaborate on thesis and we have postdocs as well. So please reach out if this is something you are interested in. There's also a lot of opportunity for getting funding through the Phi-Lab's initiatives. The biggest of these are probably the Incube project. Go on our website, phi-lab.esa.int, and check out these opportunities. So I'm not from the Invest office, so I'm not an expert on the opportunities for getting funding, but there is a lot of opportunities out there. Yeah, also internships. So reach out if someone is interested on that. Okay, and that was my last slide. Thank you.